Can the world's largest source of oxygen, I mean, the very engine that keeps our entire planet breathing, actually be suffocating?
It sounds like a paradox, doesn't it?
Yes,
An impossible one.
it really does.
We're talking about the ocean, this massive system that generates well over 50% of the air we're inhaling right now.
Hmm.
But the research is, well, it's unequivocal. The oceans are rapidly deoxygenating.
And that's what we're doing a deep dive on today, this silent crisis. Our mission is to unpack the physics, the pollution, everything that's driving oxygen levels down so much faster than anyone thought, and, what this really means for us, for human survival.
And the key thing to grasp right from the start is the urgency. This is not some future problem for, say, 2050.
This is happening now.
Right now,
Yep.
the data shows oxygen concentrations are dropping globally, and the speed of that drop is it's outstripping even the most pessimistic models. That stability we all just assume the ocean has, it's proving to be much, much more fragile.
So let's start with the most basic question. The ocean is just so vast, right? It covers 70% of the planet. How can its oxygen just disappear? What's actually happening in the water?
Well, the oxygen we need, and what all marine life needs, is what we call dissolved oxygen. DO, for short.
Okay.
So it's not like it's being physically removed. It's the concentration that's dropping. Think of it like trying to breathe at the top of Mount Everest. The air is still there, but the density of usable oxygen is just too low to survive.
So the fish are essentially gasping for air.
They're literally suffocating. When the DO concentration falls below a certain point, their gills just can't pull enough in to keep them going.
And what we learned from the material is that this isn't hitting all creatures the same way. The cost is immediate, but it's also very selective.
That's right. The most vulnerable are the big, high-energy fish. Think tuna, marlin, swordfish.
The top predators.
Exactly. They have these incredibly high metabolic rates to swim fast and grow large, and that requires a huge amount of oxygen. They're the first to feel that stress. It's like taking a marathon runner and dropping them at high altitude. They just can't perform.
But this isn't just about losing a few popular types of fish, is it? We have to talk about the systemic risk. What happens when you start pulling out the top tier of an entire food web because it can't breathe?
That is where the ecological collapse really begins. As the oxygen levels drop, these big mobile fish are forced into smaller and smaller areas.
We're searching for water they can actually breathe in.
Precisely.
Yeah.
It's a phenomenon called habitat compression. Their massive hunting grounds shrink to just these thin layers near the surface. So now you have more competition, less food, and they're way more vulnerable to, say, fishing boats.
Okay, I want to challenge that for a second. If the big predators are squeezed out, won't other smaller fish just move in and take their place? Where's the real threat to the whole chain?
That's a great question. And the threat comes from something called a trophic cascade, specifically mesopredator release.
Okay, what's that?
If you take the pressure off from the top, the big apex predators, the mid-level predators suddenly have no one hunting them.
Smaller sharks, maybe? Squid?
Exactly. Those populations explode, and they start to just decimate the lower levels of the food web, the small forage fish, the zooplankton. The entire system gets rewired to be less diverse, less stable, and that instability just ripples through everything.
Okay, that paints a very clear picture. Suffocating life, a collapsing food web. So let's get to the causes, because the material points to this really deadly combination of two main culprits. Let's start with the one tied to global climate change.
The primary driver is, of course, global warming. But it's not just that the water is getting warmer. It's how that heat affects the actual physics of the ocean.
Right, and there are two parts to this, aren't there?
Two distinct parts. First is the simple solubility effect.
This was the soda bottle analogy, which I thought was great. Warm soda goes flat faster.
It's a perfect analogy. Cold water can physically hold more dissolved gas, more oxygen.
Yeah.
As the surface of the ocean warms up, its basic capacity to hold on to oxygen goes down. The ocean is literally pushing air out. That's just fundamental chemistry.
But the second effect of the warming is, I mean, you could argue it's even more destructive, especially for the deep ocean.
Yes, this is thermal stratification.
Stratification.
So as the surface layer gets warmer, it also gets lighter. And that light, warm water sits on top of the colder, denser water below. It creates this powerful barrier between the two layers. It's like a blanket or a lid.
So it stops the mixing.
It stops it almost completely.
Yeah.
Normally you have currents and winds that mix that oxygen-rich surface water down into the deep. But with this thermal lid in place, that supply road is cut off.
Wow.
The life down in the deep is still using up oxygen, but the resupply from the surface is blocked. So huge volumes of the deep ocean are essentially being starved of air, not because the oxygen isn't there, but because the delivery system is broken.
So that's the climate piece. Less capacity to hold oxygen and a broken delivery system. Now let's get to that second major factor, the one that's tied to farming. Agricultural pollution.
This one creates these intense localized disasters. It's a vicious cycle of over-fertilization.
From farms, right?
From farms, we use huge amounts of nitrogen and phosphorus on crops. Not all of it stays on the fields. Rain washes that runoff into rivers, and all those rivers eventually flow to the sea.
And when all those extra nutrients hit the coast, what's the immediate effect?
An explosion. You get this explosive growth of phytoplankton and algae. It's a process called eutrophication,
Like a giant algal bloom.
a massive one. And at first that might seem good, more plants, more life, but it's totally unsustainable. Eventually that huge amount of algae dies and it all sinks.
And then it starts to decompose.
Exactly. And the bacteria on the seafloor have a feast. They gorge on all that sinking organic matter. But just like us, bacteria need oxygen to respire. And because there's so much food for them, their population explodes, and they vacuum up all the dissolved oxygen in surrounding water.
And this is what creates those areas the sources call dead zones.
Dead zones. It's a chillingly accurate name. And we're not talking about small spots. These can be huge areas of the coast, thousands of square miles. The one in the Gulf of Mexico, for example, is fueled by all the runoff from the Mississippi River basin.
When you say near zero oxygen, what can even survive in a place like that?
For any complex life, fish, crabs, shrimp, it's impossible. They either flee or they die. These zones are biological deserts created by us. The only things that can really thrive there are certain types of anaerobic bacteria, the ones that don't need oxygen at all.
So to put it all together, rising temperatures are making the whole ocean worse at holding oxygen and stopping it from getting to the deep sea.
Well, at the same time, our agricultural pollution is creating these localized zero-oxygen black holes all along our coasts.
It's a perfect, deadly 1-2 punch.
It is. It compromises the health of the entire planetary system, from the global scale right down to the local.
So let's bring this back to us, to the listener. The source material frames this as an environmental tragedy, but it's more than that, isn't it? This is a survival issue.
We absolutely have to. It's worth repeating that critical statistic. More than every second breath you take comes from the ocean.
50%?
50%. It's produced by marine phytoplankton. If the ocean becomes a place where they can't thrive, either because it's too warm or stratified or choked with pollution, then we are literally degrading the factory that makes our air.
Looking at the big picture, then, it's not about conservation in the traditional sense. It's about atmospheric stability.
And that's why the term silent crisis is so apt. We don't see it. It's happening underwater, out of sight. It's not a forest fire you can see on the news. It's a slow-motion decline in the concentration of a molecule hundreds of feet below the waves.
So people won't feel it until they feel it, until there's a catastrophic, visible failure point, a massive fish die-off that can't be ignored or, worse.
And the scary thing about ocean systems is that once you cross certain thresholds, once those stratification layers are locked in place or major currents are altered, you can't just flip a switch and go back. The damage becomes functionally irreversible on any human timescale.
We're betting our atmosphere on a system that we're simultaneously cooking and poisoning.
That's a very good way to put it.
Okay, so let's synthesize this one last time, the critical takeaway. Ocean oxygen levels are dropping because of heat, which messes with physics, and pollution, which fuels these oxygen-sucking blooms.
Creating these huge dead zones. And the ultimate risk is that the entire ocean system stops being the stable life support system we depend on. It moves from being a regional problem to a fundamental threat to our existence.
And the sources are clear that this is happening now and that we're approaching a point of no return.
The window to act is closing very, very fast, especially on the agricultural runoff, which is something we can actually control from land.
Okay, so that leads to the final thought. Based on everything we've just unpacked, the broken physics, the deadly chemistry awareness is clearly not enough. If we're really approaching a point of no return, what specific, immediate regulatory changes would be needed to attack that controllable factor, the agricultural runoff? What would it take to stop creating new dead zones and try to stabilize the largest oxygen factory on Earth before this silent crisis finally explodes?